In this video, we're going to uncover the derivative rules for sine, cosine, and e to the x. If you want to follow along, the links to the companion worksheet are in the description below. So let's get started. Now, most people studying this at this point have learned power rule, and most teachers will then go ahead and have you practice power rule on all sorts of different polynomials, radicals, and that sort of thing. But they're more functions than just polynomials. They're, as we've said, trigonometric functions, exponential functions, and so on. And a lot of teachers will just tell you what is the derivative of sine, what is the derivative of cosine, and e. And here, I'm not just going to tell you what it is, I'm going to show you how it connects to power rule. And it uses a concept called Taylor polynomials. Now, if you're studying calculus in high school, this is a BC calculus topic. If you're studying this in college, this is more of a calculus 2 concept. But that doesn't mean it's hard to understand. It's actually pretty easy. And if you know power rule, then the derivatives of sine, cosine, and e will seem very easy to you. So for this first one, we're given this series and it says write the next 4 terms. So if you look, we've got x cubed, x to the 5th. So we notice that the powers on x go up by 2 each time, and they're all odd. So the next one is going to have x to the 7th. Now also, we notice that this has a denominator of 3 factorial. This has a denominator of 5 factorial. Now, if you think about it, well, what is 1 factorial? Well, it's just 1 times itself because there's no number lower than that. Whereas 3 factorial is 3 times 2 times 1, and 5 is 5 times 4 times 3 times 2 times 1. And so here we have x to the 7th on top, so we're going to have 7 factorial on the bottom. Now, the other thing to keep in mind is that this term is positive, this term is negative, then this term is positive. So the next term here is going to be minus x to the 7th over 7 factorial. So that means the next term is going to be positive. So we're going to add, then the next term is going to be x to the 9th power over 9 factorial. Yeah, that's 2. We want 2 more. So now we have x. So we went from 7 to 9. So now we're going to go up to 11. X to the 11th over 11 factorial. And then finally we have x to the 13 over 13 factorial. So that's this pattern that this series follows. Now let's look at the next one. The next one is another series that looks very much the same, except here it starts 1 minus x squared plus x to the 4th. Now, you may think, well, these two are totally different because here we had an x cubed, x to the 5th. Here we don't have an x, then we have x squared and x to the 4th. What's the pattern? Well, if you think about it, when there's no x, that's the same as x to the 0, because anything to the 0 power is just 1. So actually there is a progression in the powers of x. It goes from 0 to 2 to 4. So if we want the next term, it's going to be minus x. Now they're even. So 0 to 4, this next term is going to be minus x to the 6th over, and again, the denominator matches the exponent. So it's going to be 6 factorial. Then we're going to add x to the 8th over 8 factorial. And then subtract x to the 10th over 10 factorial plus x to the 12th over 12 factorial. Now, this last one on this page, here we have 1 plus x squared over 2 factorial plus x cubed over 3 factorial. In the previous two, we were going with all odds or all evens, and now, well, here we've got x to the 0, here we've got x to the 1, 2, 3. Now we're not skipping anything, and they're all positive. So that means the next term is going to be plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial plus x to the 6th over 6 factorial plus x to the 7th over 7 factorial. So that's the next 4 terms in this series. Now at this point you're asking yourself, well, where's the power rule come in? Where are the derivatives? This just is work with series. And you're right, it is. But here's where the interesting part comes in. Because I said that this is Taylor series, as we call it. And the interesting, really cool part about this is that, according to Taylor, who was a mathematician who lived in the 19th century, I believe, what he discovered was that sine, well, sine we know is just a wave, but it can be represented as a polynomial. And that's important for us because right now all we know is power rule. So that means the only derivatives we can find are the derivatives of polynomials. So sine by itself, well, we don't know what that is, not in terms of a polynomial, but thanks to Taylor polynomials, we can look at this and say, well, we can take the derivative of that. That's just a big polynomial. So if we can take the derivative of this, and that's the same as sine, that means we know how to find the derivative of sine. Now here I've just listed out the first three terms, but this is the exact same series as the series in number 1. So just to give myself a few more terms, and I'm not going to write them all out, minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial, dot, dot, dot. So if we want the derivative of sine of x, we'll write this as d dx. So this is our notation when we want to write the derivative of this expression, so sine of x. So now, we can't break this down in any way, but using power rule we can say if sine equals this, then we can take the derivative of all this. So the derivative of x is just 1 minus, now we have x cubed on top and 3 factorial on the bottom. Now the 3 factorial on the bottom is not going to be affected, so the top becomes 3x squared over 3 factorial. And then it becomes x plus x to, 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial plus 9x to the 8th over 9 factorial. Now notice what happened. Notice that all the powers that were odd now become even. We've seen that before. But there's one little bit of simplification we need to do. Remember that 3 factorial is 3 times 2 times 1. Well, the 3 is on top. We can cancel a 3 here with a 3 here. And what that's going to leave us with is 2 times 1, or 2 factorial. Likewise here, 5 factorial is 5 times 4 times 3 times 2 times 1. And there's a 5 here. That'll cancel, leaving 4 times 3 times 2 times 1, or 4 factorial. Now if we look at this, haven't we seen that before? Yeah, we have. Let's continue. This is going to be minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. We have seen that pattern before. This expression right here is the derivative of sine, but we also know, what is this? This is the expression for cosine. Now again, a lot of teachers would say, it's this way, don't ask why, but if you look at it, we can represent this with a polynomial that we can very quickly find the derivative of and say, hey, the derivative of sine, there it is, it's cosine, and here's why. So likewise, if we've done it with sine, we can also do it with cosine. Now, I'll give myself 2 more terms, minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. So if we want the derivative, we write d dx of cosine of x. Now the derivative of 1 is just 0. Don't need to write anything there. Minus 2x over 2 factorial plus 4x cubed over 4 factorial minus 6x to the 5th over 6 factorial plus 8x to the 7th over 8 factorial. Now again, 2 factorial is just 2 times 1. And if I cancel the 2, we're just left with a 1. Now we don't need to write the 1 in our denominator. It's just negative x. 4 factorial is 4 times 3 times 2 times 1. If we cancel with the 4 on top, we're left with 3 times 2 times 1, which is 3 factorial over x cubed minus, and if you notice a pattern here, x to the 5th over 5 factorial plus x to the 7th over 7 factorial. Now, if you look at this, this should look similar, but not exactly the same as what we saw up above. It's opposite. So if we factor out a negative 1 out of this expression, we're left with x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And just to cover myself, I should put the dot 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 on the end of these because it does continue on forever. We're only looking at the first few to establish a pattern. Now this we've seen exactly. Where have we seen this? Well, we saw it up above in number 4 and in number 1. This is sine. So negative 1 times sine of x. So that means the derivative of cosine is negative sine of x. Not positive, but negative. Let me write that down here. So that is our derivative for cosine, negative sine of x. So now let's look at the last one. Our Taylor polynomial for e is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Now, I'm not going to need any more terms than this, and you'll see why. So the derivative, so d dx, this is how we call that, d dx of e to the x equals 1 goes away, becomes 0, x becomes 1, x squared over 2 factorial becomes 2x over 2 factorial, x cubed over 3 factorial becomes 3x squared over 3 factorial, dot dot dot. We can simplify this. 2 factorial is 2 times 1, cancel the 2's, and we're left with a 1 in the denominator. 3 factorial is 3 times 2 times 1. Cancel the 3's. We're left with 2 times 1. So 2 factorial. Now, where have we seen this? There it is right there. It's the exact same thing. And so every term after that is just going to become the term before it. And so the derivative of e to the x is actually the simplest derivative in calculus, because the derivative of e to the x is e to the x. And so using power rule, it's the very simplest derivative we can have. Nothing changes when you take the derivative. Everything, the first term disappears and every term just moves down 1. So, hope you like this. If you do, please give it a thumbs up. For more videos like this, click the subscribe button. If you have suggestions or other problems you want to see worked out, type a comment below. If you want to support the channel, click the Patreon link to help keep this going. Thanks so much for watching. Remember, the only way to understand something is to do it.